Yeah, I'm here to talk about Rust and Scala. It's great to be here. I love Oakland. This is my shirt. The Oakland A's are my favorite team. So it's green and gold is the colors. And so if you if somehow, I was told that the fonts render small on the screen, so if somehow you can't see it or you want to follow along, I posted a URL so that you can also look at the presentation on laptop or whatever, but hopefully that won't be necessary. I lead the PhiloDB open source project, time series database. I'm also a landscape photographer. If you want to give me a follow on Instagram, that'd be pretty awesome. It's all about the Instagram follows, right? So, I want to start by talking about how I got into Rust. Like, you might have heard a lot of things about what this thing is, Rust. So, we were basically, we've been building a time series database, an in-memory time series database, which we believe is fairly scalable. It is written in 100% Scala, and it is capable of storing up to like 100 billion data points in memory. And we can ingest something like 1 million samples per second on a single node. And this kind of thing is fairly difficult to achieve in any language, let alone the JVM, right? And we found out a lot of things the hard way. One of the things is that it's pretty impossible to achieve what we did if you just do a normal object graph in the JVM, in the JVM heap. What we found was that just the overhead from the object graphs alone was, something like 50% of the data we wanted to store, which is, for us, it's really not acceptable, right? And the other thing was that we found that we were getting really long GC pauses, because what happens if you store a lot of data for a long time is that this data starts getting into, it goes from young gen to old gen. Once you fill up old gen, the GC really struggles and starts to choke. You start getting something like 20-second pause times, something really, really horrible, right? So this is something that we actually encountered. So what do you do in that? What do you do? So we did what a lot of other projects like Cassandra and HBase have done, which is that we started moving data off heap. Now, this works. You can store data exactly how you want when you store data off heap. You have complete control, but it is also really, really hard. You're talking about managing memory manually. You have to know exactly when you allocate and free. This is not easy. And we also found that working with low-level data manipulation and having to do it at the kind of rates that we wanted to do is also really, really hard. It works, code works for the most part, but it is just really, really ugly, right? And not very safe. Last year, I came here to Scale by the Bay, and I attended a great talk by Brian Cantrell, who was talking about Rust. And at that time, I already started thinking about, maybe this is not the best platform. Just doing stuff natively in the JVM wasn't necessarily the best platform, and see if there's ways we could improve, our safety and some other things. And he talked about Rust as a language with certain values, and those values, some of them, the most important ones that appealed to me, was performance, safety, and abstractions. And he said you could pick 3, meaning you could take all of them. Usually you think about these kind of things, you usually pick 1, or pick 2, like pick consistency or pick, pick availability. And you can have one of those, right? But you can have all of them. And so I was like, what does this mean that you can have all of them? So this was really interesting. And being a native language, you have access to things like structs to allow for good low-level access, which was good. And some of the other things that was really interesting, for one, being able to prove that you have correct memory access. And also, if you look at the architectural trends that are happening, you can see that CPUs are not really getting any faster, right? The overall clock speeds have stayed the same or pretty much started decreasing. So what do you do, right? So you have more and more cores. You have to be really good at doing concurrent stuff now. And you have to start taking advantage of some of the other CPU features like SIMD, GPUs, and all this stuff. And so this kind of portends a trend towards taking advantage of the hardware in a way that's, frankly speaking, that the JVM has not been the best at keeping up with in recent times. So this got me started really looking into Rust. And the rest of the talk, I'm going to go into looking at the things that make Rust very different, and kind of comparing them with how we might do things in Scala and looking at the differences. I'm going to start with memory model. So the JVM memory model is pretty simple. You have the stack, right? And so the things that you store on the stack, this is something you don't really think about because this just happens for you. But basically, what you put on the stack and when you call a function is that you can put primitives on there, or you can put object references. And so everything that's not a primitive in the JVM is an on-heap object, right? So fairly simple. And this did not really show up, but there's basically, this is supposed to be a graph. So basically, you have an object graph, and you have a garbage collector that will clean up things for you, which is really, really nice, because the garbage collector means that it will track all your usage of objects. So if object 1, object 2, it knows how many people are using object 1 and object 2. When someone is no longer referencing object 1, then the GC knows it can clean it up. This solves a lot of problems for you that you don't have to worry about allocation, deallocation. You don't have to worry about who's using what or if something is valid. You know something is always valid because there's somebody keeping track of it. So this is really nice. Rust is quite different. Rust puts a lot of things on the stack, and it is not just primitives, but structs, which are like basically records or case classes, go on there. Anything that is fixed size, essentially, goes on the stack, as well as pointers. And the heap is used for dynamic data, for example, maps, lists, strings. Now, Rust does not have a garbage collector. How does it manage this memory, and how do you know when it's safe? That's one of the most interesting topics. So one of the principles is that Rust allows you to mutate data only if someone has unique access, which means that only I can mutate something. And if your Rust program compiles, then it is proven that it will not have memory corruption or data races. That's it. Well, I mean, yes. Like how you get there is a really interesting part. So let's look at an example. So this talk, I'm going to put a lot of code on there, which I hope you enjoy. We're all want to look at what it means. If you look at this looks pretty simple. So instead of val, you have a let. This means I'm assigning, in this case, x to a new string, which is allocated on a heap. The next one looks innocuous in just about any language. I've assigned a new variable y to x, but in Rust it has a different connotation. So what happens is that when we say let x equals string, x has become the owner of the string. And ownership as a concept is how Rust keeps track of when it is the data is valid and the scoping and when it gets freed. So in this case, after you assign x to y, the ownership has moved to y. So now y owns a string and x doesn't anymore. So in this case, printing out x after you do this, and this seems strange, but printing out x after you do y equals x is actually invalid. And the reason for that is because after x is moved into y, x is no longer the owner. So Rust can no longer prove that accessing x is valid. So access at that point has gone out of scope. Now, obviously, if you had a language where you could only move things around, and that would not be terribly useful, right? So in practice, there's a lot of what's called borrowing. So in this case, with the same first line, let x equals string. So x is again the owner, but the second line looks a little different. Y is equal to ampersand x, which means that y is a reference to x, and it's borrowing it. So when you borrow something, you can borrow something in real life as long as you can return it to the owner, right? So in this case, it is the same, in this case, after y borrows x, I can still refer to x because x is still the owner, and y y is borrowing it as long. Basically, Rust will allow you to borrow x into y as long as x is still around. So you can have a reference. You can have an unlimited number of immutable references, which means other people can read the value. But Rust will only allow you to have one mutable reference, so there's only one person that can mutate it at a time. Let's look at. So what is really interesting is that Rust is a type system that has certain traits that enforce correct usage of mutation and sharing things across threads. So I won't go into these into detail, but for example, there is one trait that will actually allow for multi-threaded ownership and sharing, which not a lot of things in the language have naturally. So this is an important concept I like to cover. This is called safety by default. And this is really interesting because originally came from languages such as Ruby and Python, and you're like, well, things on JVM like Java and Scala are pretty safe, but Rust actually, well, we'll just go into the examples and I'll explain what I mean. So, for example, this is a fairly common code. You have a val map, and we're going to create a new mutable hash map. Right, so what does this really mean? It means that this is what I call service level immutability. It means that I cannot reassign the reference that map points at. So map will always point at this mutable hash map. However, I can still mutate the hash map however I want, right? There's basically no bounds on that. So in this case, the next line, I'm adding a new key and value into this map. And this seems pretty normal code. But what it means is that the only thing the val enforces is that I cannot reassign it, but it doesn't control the mutation, right? So if I want immutability, I have to choose the right collection to use, which is immutable. Let's contrast this with Rust. So in this case, what I'm doing is, this is pretty much the same code. I'm creating a new map, hash map new. The syntax looks a little different. And I'm doing an insert, which is the same thing as the plus in previous example. So this actually does not compile because when, by default, the let is considered immutable. So the map is immutable, and any methods which tries to mutate would not work. It gives you a help message which says you can declare this as a mutable thing, in which case this would actually work. So let's do that. So I'm going to do let mute map, and now I can do the insert, and it won't complain, right? So there's in Rust, there's a difference between the objects and references. So references point at the object and allow you to, you can share them, so that's like the borrowing thing that I mentioned before. In this case, I've referred to map using the ampersand in the third line, let immute ref equals and map. And you see that in the original example, so map I can insert into map because I'm the owner. If I share an immutable reference, whoever uses it then cannot insert. So this allows me to separate out who can mutate things and who can read things. If you pass an immutable reference, whoever uses it, this would also not compile. It will give you a suggestion that maybe you want to change into immutable references, which might not be what you want to do. Let's look at a thread safety thing. So this is something that I know it has happened to me, and maybe this will seem familiar. Let's say that you use actors. Actors are great. I love actors. So you say actors are thread safe, pretty much, right? Because you cannot you can only receive messages essentially like it might not occur in the same thread, but basically you won't process two messages at the same time, right? So you always process one message, and you say, okay, so that means I can use a mutable collection, that's fine. And when I get a message, maybe I'll mutate it. And maybe one day later, or maybe your teammate will go in there and say, oh, I need to use some asynchronous thing, right? So I'm going to put a future in my actor, and I'm going to map it, and then I'm going to mutate the thing. Oops. So what has suddenly happened is that, and this is very easy to do, because this is a really trivial example that is small, but imagine if your example is real world and had 50 or 100 lines. It's very easy to do this where I'm kind of mutating a data structure in a callback, and I don't even know it. And then later on you discover that I have a horrible bug, right? So I know this is not an actor, but this would be something roughly equivalent in Rust where I've spawned another thread. And so I've created a hash map again. And in this other thread, I'm attempting to do an insert into this data structure. The only thing new here is that there is something called arg. Arg stands for atomic reference count. And it allows Rust to keep track of who might be using a data structure dynamically in cases like threads, where you don't know if one thread might end before another. So Rust will not allow you to do the mutation in another thread because arg is something that does not permit basically multiple people to try to own and mutate at the same time. And to get around this, there's different ways to do it. One way would be you can use something called a read-write lock, which would allow multiple people to actually take a lock and mutate it at the same time. So things like read-write lock have a special trait that informs the compiler that it is actually safe for multiple threads to mutate this data structure. Another way to take care of this problem, which is really nice, is that Rust just merged a new feature called AsyncAwait recently. And what AsyncAwait allows you to do is declare asynchronous functions. So in this case, I have a function called map_insert, and I put an async keyword in front of it. This means that I can run it as a future, and anything that I return, in this case, I'm not returning anything, but if you were to return something, it would be returned through a future. Now, in my main body loop, what I'm doing is I'm calling map_insert, and notice that I'm giving it a mutable reference. Normally this would not be allowed, but in this case, the Rust compiler is able to deduce that I'm calling an asynchronous function, and I'm going to wait for it to come back. So in this case, it knows that the main body cannot do something that also is mutating the map at the same time. And it also knows that this map will survive because it knows the function will return. So it's able to deduce that it's safe for you to pass an immutable reference. And as an aside, there's something really cool about AsyncAwait, which has anybody debugged stack traces that involve futures here? I'm going to raise your hand, quite a few hands. And you notice that there's really long stack traces with a bunch of gibberish about, I don't know, like something about futures or some concurrent thing, right? And you can't really tell like the previous points from which you've launched your asynchronous code. So we have asynchronous stack traces in Rust, which means that in this case, we know that foo called bar called blowup in an asynchronous way, and it can track the callers, which is pretty cool for debugging. I'm going to go over this just really quickly. There are actors, and actors is an actor library. This is sort of like Akka typed, in which case your actor can handle different types of messages. So in Rust, instead of defining a class where you implement one or more traits, instead what you do is that you implement a trait for a struct, and those implementations are separate. So I've implemented actor for summator, which is an actor definition, and I've implemented a handler for the sum message, and you notice that there's a handle method which can take results and do stuff with it. And notice that any method has a &mute self, which means that it's allowed to mutate the struct. So you can control mutability explicitly when you define methods. This is one of my favorite things that I think is pretty cool for processing data, is that there are certain safeguards for numeric processing. Rust will not coerce different types of integers like ints to longs, so you have to explicitly cast them. But I actually like this for very precise code because there are a lot of places where you might not realize that you're doing something and you might lose precision or something. And it also has signed and unsigned types, which I also find useful for ensuring the correctness of certain things, such as right shift, left shift, that kind of thing. So safety is nice, but what about this? Like, how fast can it go, and what about like abstractions, right? What about functional transforms and things? So this is something that we all use. So this is fairly important. So I'll just share this. This is actually, these are classes that are taken from PhiloDB. Like, there's nested case classes. We have a chunk query info that has an embedded chunk set info, which has a seek, which has some other stuff. So, like, I don't know, maybe two levels deep. So, and unfortunately, my graph is not showing again. But so we have an object graph here, right? The chunk query info has a chunk set info. And so each of these things in memory actually has a byte, has a 16-byte header for each object. So in this case, we end up with an overhead of about like a little bit more than 100 bytes for a single instance of a trunk query info, assuming I have like say, two pointers or something. If you have structs, they're actually laid out like C structs so that they are inlined. So in this case, the same thing in Rust, the chunk set info with a bunch of fields would be laid out right before this long data reader, which is the next set of fields. And so this allows me to eliminate most of the, well, there's no object overhead. So this allows me to save 100 bytes per thing. And if you have millions and millions of these, then that's something that adds up. Here's a simple functional transform example, and we'll go into what this is actually doing in the JVM. So this counts the number of even numbers, fairly simple, right? You do a filter and you figure out which ones are even and you count the length. So what's happening under the hood is there's actually a lot of stuff that happens. First of all functions are actually objects in the JVM. So the closures, you need to allocate a Scala.function1 for the inner closure. Then for each number, because oftentimes, or most of the time, closures are not boxed, what this means that the number needs to be boxed into a Java-lang integer. It gets passed into the closure, which has an unbox method. And then you calculate it, whether it's Boolean or not. This might get boxed again. So some of the boxing could possibly be optimized by the JVM in some instances. It really depends a lot on a lot of specifics, like how simple it is, how short the method is, how many arguments you have. But it's very easy to basically fall under this behavior if you make just a really tiny change, and you wouldn't really know it, right? This is equivalent transform in Rust. It looks pretty much exactly the same, except that it works on iterators. But you have a filter method again and your count method. The syntax is a little different, but it's more or less the same code. And in this case, Rust is actually able to transform this into a very tight loop with inlining, and there's no boxing because there's no objects, which is pretty cool. So where this points is that when you have the ability to optimize high-level abstractions with little or no cost, and to get access to some low-level things such as SIMD, leads to really fast data processing, which is pretty promising. So there's a whole bunch of really interesting projects. Some of you might have been at the Weld talk earlier. Weld is like an intermediate, like an IR that's written for data transformations to speed up everything from Spark and other libraries, and looks very promising. That one is written in Rust. And there's some other stuff out there. Apache Arrow has a new query engine, which is written in Rust. And there's some other timely data flow. It's kind of like a Spark-like distributed compute layer. So there's a couple interesting tools that have been written out there. I highly recommend ripgrep, by the way, if you want a really fast grep utility. It is super useful it will search through your whole code base. So what did I learn looking at Rust? There's a couple of interesting lessons. First of all, I think you have to expect that things will go slowly at first. It takes a while to learn, what does it mean? What does ownership mean? What does borrowing mean? And the compiler errors, there will be a lot of them. Although the error messages are useful, but yeah, there will be a lot of them. The community is very helpful. It doesn't have a repo because most native languages don't. For me personally, this is difficult because I love to use the Scala repo to develop. And I think it's kind of a balance. So I think for most people, the JVM Scala is a very good platform and probably will be more productive overall. But I think there are a lot of cases where Rust would be really, really good. And where it's good, it has like very few equals. The build tool called Cargo is really, really awesome. And so is the packaging infrastructure. And I'm sorry, it is quite a bit easier than SPT. And I think something that maybe I didn't expect is that I think learning Rust has kind of improved my programming everywhere on kind of the emphasis on safe APIs. It's a little different. You can kind of emphasize places that are safe, but it's very different when safety is universal and pervasive, like everywhere in the API. I think that makes a really big difference when you're basically forced to make choices for safety everywhere. So we see something that is very promising. The question is, how would we potentially explore or use it in our ecosystem, right? So an obvious example is way to go is to use it as a standalone microservice. But I would argue that one good way is to try to embed it. So one nice thing about Rust is that it has a small runtime. So you can create a .so or something and integrate it. And that way you can reuse, a lot of your Scala code or JVM code and kind of use it for what it's good at and use Rust for what it's good at. There's a couple different ways that you can do it. I've used JNR, which is JRuby projects. You basically, it's really simple and fast. The most promising way that I've seen, though, is Growl VM, which promises to integrate LLVM bitcode into the whole platform and give you a uniform way of debugging code, whether it's JVM or native. That's kind of something to really keep on the horizon. And finally, I've taken some hints from Rust back into our JVM code, into our Scala code. I kind of created these classes for native pointer access based on similar ideas from Rust where your basic class is immutable. You have to explicitly ask for a mutable version, and you have to explicitly kind of change bit widths to get at different types, which is just taking some of the ideas back. And finally, if you are interested, you can look at this later because I have a list of links, but there's some web frameworks and some interesting things that people have done. And there's various IDE integrations, IntelliJ, VS Code, and other editors. And I'll mention also briefly that server-side Swift is also really interesting. It's also something really interesting to look at. So thank you very much. I have a set of links that, if you're interested, these are just notes on different interesting Rust things that I've kept in mind. Yep, thank you.
Thank you, Evan. Any questions? I can give you a microphone.
Yeah, or I'll be outside.
Looks like no. Thanks, Gab. Thanks, Evan.